I start with the problem definition, and then we see where it goes. So the problem is that we want to estimate an integral, right? And that we have a distribution, and we want to estimate the expectation or compute the expectation. And well, there are many ways to do this from samples. So the simplest way is that you just take samples from this distribution and you average them, or if you don't know, if you cannot do it, so that's typically the regime of when sampling becomes interesting, then you can use different sampling methods like rejection sampling or importance sampling or many other sampling methods. Or you can also do sequential sampling, where the samples you take are not independent anymore, and you can take MCMCs and Hamiltonian MCMCs and Langevin and so on. So I could continue this if I was a sampling person, but because I'm not, these are all the algorithms I know. So there are plenty of these algorithms, and then really the question is which one should use, right? So there are all for different problems you should use different algorithms, and it's really hard to figure out which one. And usually to get good samplers, you should bring in some knowledge about the problem. So just a very quick look through of some titles. So you can find a paper like a sequential importance sampling algorithm for generating random graphs with prescribed degrees. Right? So it's a special problem. There's a special paper written for this with 200 citations. If you take another problem, meta-model-based importance sampling for structural reliability analysis. Another problem, again, another specific algorithm to solve this. Again, 200 citations roughly. And you can continue this. So you can, and these are just for importance sampling, which is one specific way of sampling. So the take-home message is that there is this plethora of algorithms, and they actually help. Like when you have this problem and these algorithms, they are not always, as we've heard before lunch, that there are some cases where if you design a generic algorithm, it can be better than a specifically designed algorithm. But for all these problems, you have specifically designed algorithms, and you just, when you have a new problem, you need to design one if you want it to perform really well. Or you need to think about how to parameterize the other ones, which one to use, and so on. Okay, so what I'm going to talk about is to find some disciplined way of choosing among these samplers. So the idea is that instead of having one sampler where we think about carefully which sampler it should be and what parameters we should use, we take a number of samplers, and then we try to decide on the fly which one we use to take the next samples. Okay, and there will be basically two parts of the talk. The first one is what I call Monte Carlo sampling, that corresponds to the IID sampling. And it's based on an ICML paper with James Neufeld, Dale Schurmans, and Csaba Szepesvári, and also some results only appeared in James's PhD thesis. And the other part will be the harder case when we try to do the same thing for Markov-chain Monte Carlo methods. So first I'm going to through the IID sampling, and we'll look at the problem definition, and then how unbiased estimators can be used, where the cost of the samples are uniform, and then we will also look at the case when taking a sample has a different cost. So if you use a complicated method, then, or even if you use rejection sampling, then getting a sample may take different time everywhere. Okay, and I will show experiments showing how this method works, and then I will do the same thing for the Markov-chain Monte Carlo case. And the idea is that we try to connect this sampling the so-called multi-arm bandits, which are sequential decision-making problems or algorithms. Okay, so again, formally, what is the problem we are looking at? It's we will have k unbiased sampling methods. So we want to compute this integral, and each of these sampling methods, they produce samples so that the expectation of the samples will be exactly this number what we are looking for, and but with potentially different variances. And if you have samplers with different variances, but with the correct mean, then what you want to find is the sampler with the smallest variance. Okay, so our goal is to design a method that sequentially obtains samples from these samplers based on some rule, and then produces an estimate of this expectation mu based on all the samples. And we want to measure the performance of this estimate in a mean square error sense. Okay, so this justifies why we care about variances. Okay, so what is really the learning protocol? So we will have some estimator y bar, and well, we initialize it to 0, and every time we choose a sampler, it, and then we obtain a sample from this sampler, and we take the average of all the samples. That's going to be our estimate. At this point, it's a uniform average. It's like each sample has the same weight, and our goal is to minimize the variance of these samples, right? Because they have the correct mean, so all we care about the variance. And an alternative way is to use non-uniform weighting of these samples, and I will also talk about it. Sometimes you can win a lot with that. Okay, now if we look at if you know about online learning and the multi-arm bandit problem, then well, here is the protocol that we have an initial estimate y bar, and every time we choose an arm, it's called method here, but we choose a method, say, and we obtain a reward yt, and we look at the cumulative reward, so the sum of all the yt's, and in this case, our goal is to maximize the expectation. Right, so it's very similar than the previous protocol. In the previous protocol, what we had that we have taken samples instead of the sum, we took the average, and it's kind of the same. Here we wanted to minimize the variance of this. There we want to maximize the sum. It seems very similar. It's actually strikingly similar. So if we look at inverts the Monte Carlo allocation, then it says that we sequentially select a sampler to find the one with the smallest variance while observing samples and paying for mistakes along the way, right? So if we choose samples with really large variance and they are really off, then it will increase the mean square error of our final estimate. Okay, in the multi-arm bandit case, we can say that we sequentially select an arm to find the one with the largest mean while observing rewards and paying for mistakes along the way. So it's very similar. Actually, it's how similar. So in one case we have samplers, on the other we have arms, and then we want the smallest variance. There we want the largest mean, and we observe samples or rewards. Like, if you replace these words, then you go from one problem to the other. Okay, so maybe there is really some close underlying relationship between these. And so before going there, I'm just going to describe in more details this multi-arm bandit setting. So is there anybody who doesn't know about multi-arm bandits? Okay, the checking question, who knows about multi-arm bandits? Okay, so it's pretty honest this time, right? I mean, when you teach, you never know. Okay, so then just quickly, so we have this, we are in the stochastic bandit setting that we have k arms. Each arm have a different distribution, which is denoted by fk, and they have their own expectation. And the learning agent selects an arm in every round of the game, and the goal is to maximize the cumulative reward which was received over time. And the regret is defined as the expected loss of how much less reward we collect than if we always use the best possible arm, right? So this mu star is the expected reward of the best arm. So in n rounds we could get n times the mu star, but instead of this we just get this sum. Okay, and we want to keep this small. And it's well known that one can rewrite the regret in this form, that we, for every arm, we take the average number of times or expected number of times we chose that arm, and then we multiply this by the gap with the mean. Right? Every time we choose a suboptimal arm, on expectation we just lose mu star minus mu k. Okay, so this is fairly standard. And there are many existing theoretical results and many algorithms, lower bounds, upper bounds. So basically everything is known about this problem. And then we can look at the regret of the Monte Carlo allocation strategy. So we can define it in a similar way. So what is our goal? Our goal is to minimize this quantity, so this y(n bar). I'm using this. So y(n bar), can you see it? No. Okay. Okay, so y(n bar) is our estimate. We want it to be close to mu. So we want to minimize this y(n bar) minus mu squared. Now what is this? This is really just the variance of this y(n bar). And as such, it scales like it's a sum of n variables. So roughly it should scale as 1 over n. Right? So that means that if we compare this to if we always choose the best arm, then we would get a mean squared error of sigma star squared. That's the variance of the best arm. So we want our variance to be close to this best arm, to the best variance. Right? But this scales as 1 over n, right? Because we average it over many samples. So it's natural, if we want to compare it to sigma star squared, that we need to multiply it by n. Right? So then we get two things which are constant, and then we define the regret as basically n times this quantity. Okay, so what we do, we want to phrase the whole thing in the similar regret setting. Just because the regret, it doesn't go to 0. The regret usually grows sublinearly. So that's why this guy is roughly constant. Or actually, if this converges, so if we manage to choose the best term almost all the time, then this difference would go to 0. Right? If we always choose the best term, then this would be exactly sigma star squared, and this would be 0. And every time we make a mistake, this is slightly bigger. But if we choose most of the time the best sampler, then this difference should go to 0. Is it clear?
Yes, so maybe where does the n outside of the expectation come from then?
This one, because this goes to 0. So if you look at the variance after n samples, then with the best arm, then it would be sigma star squared over n, right? And this guy here is roughly, again, some sigma squared over n. And so if we compare it to sigma squared, then we need to multiply it with n.
And this is the average, okay.
And this would still go to 0 in an optimistic case. And so this is like the average regret. In the Bandit case, the average regret goes to 0. And so we make this to be the average regret. Okay, and when we say consistency, then this thing should go to 0. Okay, so this is how we define the regret. And then we can do a similar regret decomposition as for the Bandit case. So what happens in the Bandit case, we looked at how many times we chose each arm. So here we look at how many times we choose each sampler. And then the regret, which if you go back, so like it would be n squared times this minus n times sigma squared. Okay? So then the regret can be written as the expected number of times we choose a sampler k times the gap in the variances. Right? So in the Bandit case, we had the gap in the rewards. Here we have the gap with the variances. Otherwise, it's the same. Right? So this suggests that we can actually use the multi-unbanded problems to solve this, right? The only difference is in one case we had the reward, in the other case we have the variance. Okay, so what can we do? That we initialize a bandit algorithm, and then in every round we use this bandit algorithm to select an index. So these f's, these are the distributions of the rewards. It's not important, the notation. So we select an index, get an index from this bandit algorithm, and then we obtain a sample from a sampler. Right? So this yt, this is the sample coming from the it sampler. And then we should feed the bandit algorithm with actually the variance of this sample, right? Right? That was in our decomposition. Like the variance is the same as the reward. But if we look at the variance of this yt, what is the variance? Well, look at the negative variance, just because in one case we want to minimize, in the other case we want to maximize. Okay, so if we want to minimize, the variances, then we want to maximize the negative variances. But the negative variance is just the negative second moment of y plus mu squared. And because mu is the same for all arms, therefore it doesn't matter whether we use this mu square or not. So we can just forget about it, and we couldn't even use it because we don't know. But we can just leave it out, and then we can feed the bandit algorithm with negative yt squared. Okay, and then what is very easy to show, and I mean, more or less I showed it, that the regret of this bandit algorithm is exactly the same as the regret of the Monte Carlo allocation, the way it is defined. Okay? And we can flip this thing over, and if we have a so if we want to solve a bandit problem, then we can use any Monte Carlo allocation strategy, and instead of taking so previously we took a sample and we took the negative square. So here we can take the negative of that thing, what we observe from a sampler, and take the square root. So this works for bandits with negative rewards. Okay, but if you have the standard case when the bandits are, say, in a bounded, the rewards are in a bounded range, then you can just shift them. But this direction is less important because typically we have well-designed algorithms for the bandit problem and more heuristic algorithms for adaptive sampling. So we care more about the other direction. And again, we have that the regrets are the same. Okay, so what is the summary so far? That we have basically equivalence between bandit problems on the negative half-life and this Monte Carlo allocation problems. And this means that all the bandit algorithms which are there, they transfer. So they can be used to adapt to sequentially select which sampler to use. And all the upper bounds on the regret, they transfer. And depending on what scenario you want to look at, like individual, like gap-dependent bounds, you get the log. Minimax bounds, you get the square root. And
so is it possible at all to improve this by using the fact that you want the negative half-life as well? Does that?
No.
So if you have two bounds, that helps a lot, but on the possible rewards, right? So for bandit problems, if you know that they're all kind of bounded above and below. Right?
Well, I mean, but if you have like bandit rewards between 0 and 1, then you have all these bounds, and then it's just a translation. Right, and also the lower bounds transfer. So basically the whole bandit theory we can use for Monte Carlo allocation, and so we are going to use it in a few simple settings. So the first experiment I'm going to show is a synthetic two-sampler setting. So we will have two samplers, and we will use different bandit algorithms. So it's a question, there are many bandit algorithms, they have different qualities. It's a question which bandit algorithm we should use. And in the bandit case, usually the worst case distributions are the Bernoullis. But here we have samplers, and in the samples, if we have the same expectation and you want to look at Bernoulli distributions, then they would be the same, right? So with the Bernoulli, if you fix the mean, then the two distributions are the same. So instead of this, we are looking at, to simulate more what we see from sampling, we are looking at what we call like scaled Bernoullis, that they have a mean 1/2, and we add plus minus 1 times some s, which would be the variance or the standard deviation. Okay, so we are looking at two samplers with different s values, with different variances and the same mean. And what we find that, so we have two arms, and this is the variance of the better arm, or better sampler, and that's the difference in the variance. And what we can find that this UCBV algorithm that behaves the best among this. So that's a UCB algorithm where the variance comes in as a constant in the confidence bound. Okay, so it basically adapts to the variance. It doesn't work with the maximum value of the rewards or the range of the rewards. And in this outer regime, so when the difference is large, or the variance of the initial algorithm or the better arm is also large, then Thomson sampling becomes better. And the reason for this is that Thomson sampling has a huge variance, and so when this variance is not too large compared to the other variances, then it becomes better. Otherwise, this UCBV becomes better. And interestingly, for example, the KI UCB is inferior to in all our experiments. But if we look at, so here we can see the number of actions, and we can see the number of suboptimal pools, which basically corresponds to the regret, and we can see that all the algorithms, they are fairly close, although the Thomson sampling and UCBV, they are better than the others. Okay, and we are also going to use this for pricing European call options. So without going too much into details, the idea is that there is a stochastic model describing how the prices change. And to get the value of the option, you need to simulate many of these sample passes. And the idea of effective algorithms, which are like here we chose the population Monte Carlo method, and we use different importance sampling proposals, and the idea is that because you care about more sample passes which arrive above the strike price, you want to bias a little bit the sampling to the positive. This is this theta, and what we are looking at, that we use 16 different values of the theta and look at different strike prices. And okay, so these with the triangles and the dashed with the triangles, they correspond to the population Monte Carlo, and the dashed line is an even better estimate which uses averaging over theta in a really specific way to this option pricing. So this dashed line is really a specifically designed algorithm for this problem. And we can see that in all of these cases, we are like Thomson sampling, which is the best bandit allocation here, is better than even this specifically designed algorithm. Okay, so this shows that that instead of trying to get some new algorithm for the problem, even if it uses prior knowledge about the problem, it might be better just to take some standard samplers and tuning their parameters using Bandit algorithms. Okay, that's the take home, and this works really well.
So a question. So you always assume that you only have a finite amount of possible strategies here.
Yes.
But in adaptive MCMC, for example, usually have you can take your parameters arbitrarily, so you have an infinite amount of choices.
That's definitely so. If you have an algorithm which is able to adapt over like uncountable parameter space, then probably it will be better. But I mean, if we look at the literature on this problem, like we even tried more theta values than in the paper where they introduced this population Monte Carlo for this problem. It's like I'm not claiming that, like this is one of the major limitations. That's one of the open problems. If you can do this better. But if you want to extend it maybe to infinitely many arms, then it's better to assume some structure of the arms. And okay. By the way, here in this bottom line, basically the lower these blue bars are, the better this sampler is. So here the middle theta values are better, and as the strike price goes up, we want to bias the sampling towards higher and higher prices so that the larger theta values become better. So far we only consider the number of samples we take, right? But for example, if we use rejection sampling, then we try several samples, and at one point we get a sample which works, right? And the time to get this sample is not deterministic, and depending on what proposal we use, this time may vary. And in many other cases, if you use some more complicated sampling method, then getting one sample takes different amount of time. So in this case, we are going to look at how things change if we actually consider that different samples may take different time to get. Okay, so formally the problem definition at the beginning is the same. So we will have k sampling methods, and we want to, and they are all unbiased, so each sample has the correct mean. They have different variances. But when we pull an arm or try a sampler, then we actually observe a pair, xd, where x is the sample, what we want to get with the expectation mu, and d is the time, how long it takes to generate the sample. Okay, which may also be random. And these may or may not be independent. Okay, and then our question is now the equivalent of what is our regret, or how well we can sample with a given number of samples. This was before, but now because the time comes in, we want to look at some continuous time, and we want to look at the estimate, like the mean square error of our estimate after any given time. And if sampling takes long, then during this time we will take only a few samples. If samples is fast, then we will have many samples. Okay, and we have some technical assumptions on the sampling time, that it cannot be 0, and some other things that I'm not going to talk about. And then for any t, we can define the best sampler, or for any t we can define for each sampler, if we just use that sampler, what the mean square error would be. This is the LKT. And then for any time t, we could select the best sampler. Okay, and similarly to the previous case, we can define the regret. So what was the regret before? It was basically the variance of our sampler minus the variance of the best sampler times n squared. That was the regret. Now instead of this, we will have t squared. Okay, so it's pretty straightforward. And the problem, a slight problem, is that the optimal sampler may change from time to time. Right? So maybe the best sampler doesn't return any sample in 1 minute, then it cannot be the best sampler for 1 minute. Right? But maybe it's going to be the best sampler if we sample for 1 year. Okay, but what follows from renewal theory, that if we use a sampler for t time steps, then essentially if the expected time to get a sample is delta, then basically we would get roughly t over delta samples. And so the mean square error, the expected mean square error of this sampler would be roughly sigma square over t divided by delta. Okay, or if I reorder, it's going to be delta, which is the expected sampling time, times sigma square over t. And so this means that if we have a sufficiently long time, then this approximation is close enough. And then we can order these samplers based on this quantity, this delta times sigma square. And we can declare the best sampler, and on the long time, the best sampler will really be the one which minimizes the delta sigma square. Okay, and now what we do is basically what we had before. So we need to create random variables which look like delta sigma square, and we want to minimize the sum of delta sigma squares. Roughly, this is the plan. And how can we do it? So if we use 2 samples instead of 1, then we taking the difference of these 2 samples and squaring them. That would be an estimate of the, it's actually twice the variance because we have independent samples. And if we look at the average of the sampling times, then it's going to be an estimate of the sampling time, the expected sampling time. So we can do this if the d and x are independent, then we can take the product, and the expectation of this will really be delta sigma squared. If d and x are dependent, then we can use a third sample and say use just the sampling time of the third sampler here. Okay, so with 2 or 3 samples, we can actually create random variables whose expectation is this delta sigma squared, what we want to minimize. And then, okay, so with the negative sign, the expectation is really correct. And then what we can do is that we can run Bandit algorithms on these random variables, okay, in a similar way as before. And what one can show, this proof is much more complicated than the previous one. That one can show that the regret will be roughly, okay, this should have been t, so that n. So that the regret is roughly a square root of the total sampling time up to logarithmic factors. It's a much more complicated result. And although we have Bandit algorithms with a logarithmic regret, here because of this concentration, the need for concentration for the number of poles, we get a regret which scales as a square root. Okay, and so let's look some interesting things here. So one is that, so say we have this example that we have two samplers with a distribution. So the first one, it has a variance 1 and sampling time 2. And for the second one, we have variance 100 and sampling time 100. Right, so this means that this delta sigma square product for the first one is 2, for the second one it's 1. So basically the first term is inferior to the second one, right, because we care about this product. So it shows that if looking at the variance in this case, it's not adequate. So it has the smaller variance. Right, so here we prefer the second term. And the other observation we can have that taking the mean of all the samples, it might not be the best thing to do, right? So if we have some samples from sampler 1, they are much better than the samples from sample 2, right? Their variance is much smaller, so we should give them a bigger weight. Again, and actually, if we change the problem a little bit, so that we set the sampling time of the first sampler to 1, And we look at like similar variance and sampling time for the second one. So if the variance is d, then the sampling time would be 1 over d. Then these two arms would look exactly the same. So this delta sigma square is just 1. Okay, and then one can show that in this case, if we use uniform weighting, then we will have a linear regret. Okay, and here we can see, so in this graph here, this lambda is the weighting, how much more weight we give to samples from one arm to the other. Because any bandit algorithm, it would sample equally both of these, right, both arms. And by the way, an assumption of the previous theorem was that the optimal arm is unique, or the optimal sampler. Okay? So then in this case, one can show that we have linear regret. So if we look at, so this lambda is the weight between how we weigh the samples from one arm or the other. And one can see that even as the weight goes close to 1, the variance goes up really. And just when it reaches 1, it drops down to 0. Right? So if we only sample one arm, then we always get an optimal performance. But if we sample two arms and not use the correct weighting, then we get a really large regret. Okay, so this is kind of surprising. So the solution for this is that roughly we need to weight each arm proportional to 1 over the variance. That's the optimal weighting, and then one can estimate the variance and also give some confidence bounds on the variance. And if you use this as a weighting, then we can actually prove a similar version of the previous theorem, so get the square root t regret. Okay, so another example is another sampling method. It's called adaptive annealed importance sampling. So we want to compute some logistic regression, some normalization constant for logistic regression problem with different number of samples. And we use 3 different samplers, one which takes like 400 annealing steps, the other 2,000, and the last one 8,000. So clearly getting the samples from the different samplers has a different time. And so these are depicted here as like arm 1, 2, and 3. And the one which is not shown, that's the optimal arm. So in this case, when we have 5 samples, then the optimal arm is arm 1. And this is the regret relative to this optimal arm. And we can see that if I change the sample size from 5 to 10, then now the optimal arm is arm 2, arm 3, right? And if I take the next one, then the optimal arm is arm 2. So for all these setups, we have, as I change the sample size, the optimality of the arms change. But if you look at the bandit algorithms, then they are always better than the second arm. Summarizing what we had so far is that we looked at these Monte Carlo samplers, and we showed an equivalence between the multi-arm bandit problem and the Monte Carlo allocation problem, and we showed regret bounds and algorithms. And for the non-uniform cost case, we showed the square root of n regret, and this is just, as I said, that we can reweight. If we look at the weighted estimator, then we can get the square root n regret for the non-uniform sampling all the time. Okay, and it has real practical advantages. Now there are many limitations or potential extensions. For example, using that if we use importance sampling and we take one sample from one proposal, then it gives us information about other proposals. We don't use it. Or as you asked, we could deal with a large number of samplers, which we don't. And the last, which I will talk about in the rest, that what happens if we have non-IID samplers. So these IID samplers are nice, but in practice people use rather use Markov-chain Monte Carlo samplers than these IID samplers. Okay, so how can we extend this to this dependent sample setting? Right, that's the question. And so here I'm just rephrasing the problem. So we want to compute the expectation of some function in a higher dimensional space, and we know up to a constant the density. Okay, this is the typical case, and we want to get the normalization constant. That's a typical application of MCMCs. So this p hat, that's the unnormalized density. Okay, and then similarly to the IID sampling setting, we need to select the proper MCMC method, and we need to find the best parameters. And then the idea is the same, that we want to run multiple versions of MCMC algorithms and choose among them in a principled fashion. Okay, so what are the challenges here? So this is how these, so I have basically a distribution with 4 modes, where 2 modes are very close and these other 2 are relatively far. And the different colors are runs of different, I think just Metropolis Hastings samplers. And what we can see that, so the first question is that these samplers, for them it takes a lot of time to explore the whole space. So if in practice they don't do it, so how can we measure the sample quality? Previously we measured it with the variance, but what's the sampler which minimizes the variance? That it picks always the same point, right? So it clearly doesn't make sense. So it's a major question how we measure the quality of samples. And so because these are not unbiased anymore, the variance is not a proper measure. And also chains can get trapped into certain modes for a very long time. So that means that maybe one idea is that instead of trying to get one sampler which goes all around the space, we want to get multiple samplers, and these multiple samplers explore different parts. Right? And then we could just put together the samples, but then we have the other problem that's like this green one, for example, that some really explore more parts than the other, and then they mix up everything. So it's a pretty complicated problem. And then if we manage to somehow to fix these and get samples from multiple chains, then even the question is that how should we put together these samples? So if I have 100 samples from a really low probability region and 100 samples from a really high probability region, how do I know this based on the unnormalized density? It's not that trivial. Okay, so one way to measure the sample quality is basically it's a goodness of fit type of measure. It's one recently introduced is the kernel-Stein discrepancy. So it has a really ugly definition at the beginning. Well, okay, so it comes from a very generic definition of distances, that we want to look at the distance of two distributions, Q and P, are measured on the supremum of the expectation over a certain set of functions. Okay, and this is very generic, so this can create like the total variation or the Wasserstein distance and others. And the question is that how can we select this set of H so that we can compute this, and it would be meaningful. And the idea is that we want to select this function set such that this expectation is 0. Okay, this expectation is complicated because it depends on the true distribution, so we cannot really compute it. So we just choose a function class which cancels it. And for this, one can define the Stein operator and show that if you take some reproducing kernel Hilbert space and you transform the functions from this Hilbert space with the Stein operator, then the expectation will be 0. The nice thing is that this operator, it depends on the gradient of the log. So it basically cancels the normalization constant. Right? So we can compute this operator without knowing the normalization constant for the density. And then we can define a kernel based on the density function and the kernel for this reproducing kernel Hilbert space, and it will define us a measure which is called the kernel-Stein discrepancy, which measures basically how well some samples fit to a distribution. Okay, but it measures nicely, but only locally. So depending on the kernel width, it measures the match locally, but if you have another mode, for example, really far, then this measure won't be able to notice it. So for example, if you have a multimodal distributions with two modes, and you take samples from one mode, and the two modes are far, then this measure can get really close to 0, even though you didn't sample anything from the other mode. And it does the same thing if you have samples from both modes. Okay, so this is a good measure locally. But we are looking at, when we are looking at Markov chains, that we look at their convergence, then basically we are happy if they are locally okay. So we are going to use this. And then, so I'm just gonna build up the models for each problem I highlighted, and then see how we can address these models. So this first kernel-Stein discrepancy, that's a viable solution for measuring the sample quality. Okay, the next one is that we can consider the simple case that we have multiple samplers which mix over the whole space. Okay, and then in this case, I assume that this kernel-Stein discrepancy gives a good measure of convergence. And so we can just say that we want to minimize the kernel-Stein discrepancy, so we can use a Bandit algorithm more or less over the kernel-Stein discrepancy to select from among the samplers. Okay, but here is another problem, that this kernel-Stein discrepancy, it has this matrix form, so computing it is quadratic in the number of samples. So if you have many samples, then just making this selection would take a lot of time. So therefore, what we are going to do, that we approximate this kernel-Stein discrepancy by computing it over like small blocks of samples. It's like a diagonal approximation to this matrix, kernelized data matrix. And then, so I break up all my samples to small blocks, and then I average this discrepancy, and that's going to be my estimate. And with some experiments, we can see that this blocking, it really reliably keeps selecting the best sampler. So if I look at the kernel-Stein discrepancy computed on like 2,000 samples, then it almost always chooses the same sampler as if I look at the sum over blocks of size 10 or 20 or 100. Okay, and when it makes a mistake, then the two samplers are really close to each other in quality. So we are going to use this, and the added benefit is that now we have this summation form for the kernel-Stein discrepancy, which even better fits now the bandits, right? Because the kernel-Stein discrepancy itself is not a sum of things. So in this way, we both win in complexity, and also that we can directly use Bandit algorithms to minimize this. So a relaxed problem will be that we want to minimize this block kernel-Stein discrepancy, or the regret, relative to that. So for that, we can just use a Bandit algorithm, which is fed by these block kernel-Stein discrepancies. And then one can easily show that if we had IID samplers, then this would give then we could get a direct regret bound and also an approximation error from the blocks. Okay, but we already discussed that it doesn't matter much. So this will be our component algorithm, that if we have multiple samplers exploring the same apart, then we can use a Bandit algorithm on them. Okay, and if we look at a unimodal distribution, so it's just a Gaussian, and then these are different samplers. I think they are Mala samplers, the one which were discussed before lunch. And so these dashed lines are the Mala samplers, and these are the different Bandit algorithms. So they tend to get to the better ones. And also this purple one, that's the no U-turn sampler. It's a really nice adaptive sampling algorithm, which works really amazingly for unimodal distributions. And well, it's always better than the average of these Mala samplers, but it's because the Mala samplers are much inferior. Like you can see that the best Mala sampler is really far from the performance of these nuts. And interestingly, there is another algorithm which just computes the whole reweighting of the samples based on the kernel-Stein discrepancy, and it is much better. This is 2 dimensions, so it's much better than anything else. But this is up to 5,000 samples, and if you go to 10,000 samples or more, then it quickly becomes computationally infeasible. And also, this graph here shows the dependence on the dimension. So it shows that as the dimension increases, then this deteriorates, and eventually it seems to get worse than at least not. Okay. So the next idea we consider is if we have multiple regions, and in each region we have some samplers which mix within those regions. Like you can think about that we partition the space, and for each partition cell we have IID samples. Okay, and then okay, so that's the simple case if we have one sampler for each region, but there is also the complication if we have multiple samplers in each region. And then what we do so the question is that now we take samples from each region, and how can we combine them? Okay, and to combine them, we need to estimate the probability of the regions. Right? So if we know the probability of these regions, then basically the estimates for each region should be weighted by this probability. So we need to get a weight estimator which converges to this probability, at least asymptotically. And if we do it, and we can have good estimates locally, so this is what I call locally mixing samplers, then we get a good estimate in the end. Okay, so what is the algorithm then? The algorithm is that every time we select a region, and in this region we use a Bandit algorithm over the chains which are in that region, and use it for sampling a block of samples. Okay, and then in the end we average with this weight. Okay, so one question is how we should select which region to sample. And to this, we look at an upper bound on the kernel-Stein discrepancy. And using convexity, we can see that the total discrepancy of all the samples is bounded by the weighted average of the discrepancies over the different regions. So then we could have a few ideas how to sample. So one would be sampling proportionally to the probabilities, right? If we sample proportional to the probabilities, then we don't need to reweigh the samples. Okay, or the other thing could be that we want to sample uniformly well. So we want to choose a sampler for which this product, this weighted Stein discrepancy is the largest. Or we can choose another one that we proportionally choose with probability proportional to the weighted Stein discrepancy. Or using stratified sampling ideas, we can just choose based on the weighted variances. Okay, and this figure shows different choices. So here we know the weights. And here, if we know the weights, then we can see that the weighted, that there is a different ordering among these choices. But if we don't know the weights and we just estimate the weights, then basically all of our methods behave the same. This bad one, this is just there for reference, that's uniformly sampling. Okay, so this shows that it doesn't matter much which region sampling method we choose. And then the last ingredient, almost the last, second to last, is the weight estimation. So the question is how can we estimate the weights of the different regions? And the approach in the literature is to fit some parametric distribution, and if you fit it, then you can compute the normalization constant. But here we take another path because you need to get the right distribution, and we will use Rényi entropy. So what is Rényi entropy? It's just the expectation of basically the density to the alpha. No, take the log and 1 over 1 minus alpha. Now if we are doing this over region A, then here we just have the conditional density in that region. And then if I reorder this equation, then I get that and instead of p, I only have access to p hat, which is c times p. And so if I reorder everything, then I get that the log of the probability of the region times c can be obtained as the difference of the Rényi entropy and this expectation of the density, the unnormalized density to the power alpha minus 1. So the second term I can estimate from the sample. Right? So I take the sample and I compute the unnormalized density and take the average. And for the first term, there is a very beautiful theory of estimating Rényi entropy based on spanning trees and graphs. If you don't know, then I suggest to read it because it's really nice. So you can use this algorithm to estimate the Rényi entropy. And once we have all these estimates, so they are asymptotically, they converge to the proper values. And then from this, we can just get an estimate of the density of the density because we can cancel the constant c. Okay, so this way we can compute the weights. And there is the last problem we have. So we already considered that we have multiple chains exploring the same area and how to put together the samples, but we didn't look at that one chain can move from one area to the other. Okay, and to do this, we basically look at that in the last batch which chains were close together, and we treat them as exploring the same area, and we run the Bandit algorithm there. And in the end, when we have all the samples, then we just cluster all the samples, and for each cluster we compute the weight and we reweight everything. Okay, so that's the final algorithm, and the results are actually really good. So in this case, we are using nuts as base sampler because that's the best sampling algorithm we have, and on the left hand side. We have a unimodal case, and these are all the nuts algorithms here. And we can see that the Bandit algorithms, they don't lose too much. Like using our algorithm, it doesn't lose too much in this case. But when we have multiple modes and the modes are far, then these are all the nuts algorithms. And basically these are our algorithms with different choices of Bandit methods, so they are massively outperform any of the nuts algorithms. I think in the case when these algorithms are not able to move from one mode to the other. Okay, so based on this, I would recommend to always use this algorithm because if it's unimodal, then you don't lose too much, and if it's not, then you can win a lot. And yeah, that concludes my